Okay, in the previous video we spent considerable amount of time starting with the differential rate law of a first order reaction, and then I walked you through how to do the integration. Not something you need to know for this class, but helpful to understand where these things come from, and we derived this integrated rate law, and then we used it a couple different ways. We plotted it and we used a graph of real data to evaluate whether or not it was linear. If it weren't linear when we plotted natural log A versus t in the form of this expression y equals mx plus b, then we said it was not likely a first order reaction. From that we could also determine what the slope of that was if it did fit, and that would give us our rate constant. We determined what the half-life was, and we solved for that. And we also used the integrated rate law to actually just put in values for a particular rate constant, time, an initial concentration to figure out what the final concentration of the system was. So those were all the different ways we did that. And here I'm showing you a nice table that collects the three general types of reaction orders that we're at least going to deal with in this class. Remember, I mentioned in the first video of this series that these can actually be fractions, they can be negative orders. It gets more complicated, but you always start with the simple ideas. And the simple idea could be zeroth order, which means that there's no dependence of the rate of reaction on the concentration of the species. Doesn't have any dependence at all, which is what you see in the integrated rate law. I'm not going to derive that. We're just going to do that on the first order. And second order, like we talked about before, is a differential rate law that looks like this. And then if we were to integrate that, we would get an expression that looks like this. But the same logic applies. Now we have this suite of tools which allows us to, one, determine what the order is using graphical plotting of real experimental data. Right, if we wanted to figure out if it was first order, we would do exactly what we did in the previous video. We would take natural log of the concentration versus t. If it's straight, perfect, first order. If it's not, then it's got to be one of these two, at least in this class. And once you're in Excel and making those plots, it becomes really easy then to do something similar. So if we look at the second order integrated rate law, it's also in the form, conveniently, of y equals mx plus b, where we have 1 over a, that's our y term, we have t as our x, k is m, and then b is 1 over a naught. So now we can make a plot of 1 over a versus t. If it's a straight line, now we know it's second order. And if neither of those work, then we can make a plot just of a versus t. If it's straight, then we know it's zeroth order. So we can do all of these things. Once we know the order based on that first graphical analysis step, then we can use the integrated rate law along with the computed k, which we get from the slope of those plots, to actually figure out what the concentration of a reactant would be after some amount of time. That's the utility in how to do this. Okay, so let's use real data to figure out whether or not it's zeroth, first, or second order using the graphical logic that we have employed thus far. So this is real data that we have. What do we need to do? What sort of transformations do we need? And what sort of plots do we need in order to make these determinations? So probably the place to start is this linear graph region, right? It's already telling you this. You can figure it out from this integrated rate law, but if this is zeroth order, we need to make a plot of A versus T. So we already have that, right? We have the concentration versus T, so we don't need to do any transformations to figure out zeroth order. We just need to make a plot of these two things, which we'll do. For first order, we already have done this, right? We need to do a natural log transformation of this column of data so that we can plot natural log of A versus T, so we should do that. But while we're thinking about it, let's think about what do we need for second order. Second order, we have this 1 over A term, so that means we need another column of data where we transform this into the reciprocal, so we do 1 over that value. So let's do that really quick. So as per usual, start by just naming your column. So I have natural log of this value, and I have 1 over this value. Now we need to put in our natural log formula is just equals ln, and then I select the value. And the reciprocal is even easier. It's just equals 1 divided by this original value, enter, and then click and drag. And so now we have everything in the form that we need it in. Now we just need to make these 3 different plots and see which one is a straight line. Okay, so I made the 3 plots. So the first one on the left is our 0 order. So that's simply a plot of time on the x-axis versus the concentration, no transformations. And we see this is definitely not linear. So this is not a 0th order reaction. Similarly, this is the first order plot where we have natural log of that concentration as a function of time. That's also got this kind of concaveness. That's not what we're looking for. That's not a linear fit. And then our second order fit is the reciprocal 1 over the concentration of C4H6, also versus time. We get this nice straight line. So that allows us, if we want, we've identified now, yep, that's a second order reaction. We can go to the trend line options here and we can figure out what, we already know the R squared is going to be nice just by looking at it, but I can figure out the equation of that line because remember the equation of that line, the slope there is going to give us our rate constant. So now that we determined this is second order, we've made our linear fit, we have the slope, we can look at this and say, oh yeah, there's the slope, that's got to be equal to k, so m is equal to k, which is equal to 0.0614, and now we just need to work out our units. So just like we've done before, I like to write up just the original rate expression or the rate law, which is up here. I just rewrote it down here, but I like to do it in terms of my units. So I know the rate is always going to be in the concentration per unit time here. Our unit time is in seconds, so that's going to be moles per liter per second, or big M, molarity per second. And that's equal to K times the concentration of that thing squared, because it's second order, which means that this unit is actually going to be molarity squared. So we need our K to have units that yield this when multiplied by this. So what would that be? Do a little bit of mental algebra, and I can say, well, I need a second on the bottom, so I'm going to have 1 over seconds, and I need to get rid of one of these molarities, so I'm going to have another one of those on the bottom. So this is going to be my rate constant in units of 1 per molar second. Remember, this is moles per liter whenever I write a big molarity like that, so this is equivalent to then liters per mole second if I were to do a little rearranging with algebra. So that then would allow us, if we wanted to feed that constant back into an integrated rate law and figure out after some duration of time what the concentration of our species is. So that's really the full sequence that I'd like you to be able to do, is evaluate what the order of the reaction is given some experimental data, or maybe even collect that experimental data yourself. Once you know that, evaluate what the rate constant is, and in this case we can actually figure out now what our initial concentration is, because we know that B here is 1 over A naught. So we would be able to figure that out and then use those constants, those values, in the integrated rate law to figure out how much of something is there at the end of a particular reaction or after some duration of time. That's the sequence that will be really helpful for this version of kinetics, how we're thinking about the rates of reactions.